Got it? All right, let's get started. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this afternoon. Thank you for these students. And I just pray you be with us, help us to glorify you in what we do here this day, Lord. In your name I pray. Amen. Okay, so I'm going to pick up here, start with a proof of the chain rule. I'm going to try anyway. So here's a little theorem that we've been using. It's the derivative with respect to time of a function of two variables composed with, say, a path was equal to the gradient of the function evaluated at the path dot product with the RDT. So that's the chain rule, one of the chain rules that we know and love. And here it's assumed, what's our assumption? We assume that f is differentiable at r of t, right? Or at least near it. And we also assume that r prime of t exists, right? Okay, so proof. Let's see if we can't give an argument for why this is true. So let's pick a point. Let's say t equals to t naught, all right? Where r of t naught is equal to, let's say, ab, all right? So let's focus our attention on a particular point in the domain. And let's also develop some notation here. Let r equal to, let's say, h1, h2. I usually use x and y for these, but I'm going to use h1 and h2 so that the proof is maybe a little bit easier to follow. Okay, so what does it mean for f to be differentiable at r of t? Well, it's differentiable at r of t naught, which is equal to ab. What's that tell me? That tells me that I can write f of x comma y as equal to f of a comma b, right? Plus what? Well, plus the x derivative at a comma b times x minus a, plus the y derivative at a comma b times y minus b. Now, and then plus some remainder term, right? Whereas we discussed, if you're close, if you let x and y approach ab, then that remainder term goes to 0 in a precise way as is described by the Frechet quotient. Basically, geometrically, to get to the heart of the matter, the graph of the function is well approximated by the tangent plane, right? Where the tangent plane is obtained by just, if you look at these three terms, you set them equal to z. That's the tangent plane we talked about last class, right? So I have this approximation of the function of two variables like this. Then what happens? So we have a little bit more than this, though, right? But we have x is equal to what? X is equal to h1, right? X is equal to h1 of t. Now, if h1 is itself a differentiable function, that means I can approximate it as follows. I can say h1 of t is really h1 of t naught plus t minus t naught times h1 prime of t naught. What is that? That's the tangent line approximation for the first component function of the path, right? That's just the linearization of h1 about the point t naught. And then, of course, there's also some remainder term, right? Some remainder term in h1, which we don't, I mean, that will go to 0 as t goes to, the remainder term in h1 goes to 0 as what? As t goes to t naught. But I have the same song and dance for y. See, because y, if I have y equal to h2 of t, well, that's h2 of t naught plus t minus t naught, h2 prime of t naught, plus the remainder of h2, where likewise so I have all these linear approximations of the function, the multivariate function, and also the component functions of the path, right? And we're trying to derive this chain rule we've been using. Why is it true? It's true because if you put the linearizations together, out pops the formula. Let's assemble the pieces now. So what I'm going to do is simply this. I'm going to take this expression up in here, this guy, and I'm going to plug that in for what? Well, I'm not been quite lazy enough yet. Sorry, guys. I need to be more lazy here. I'm about to be not lazy in a bad way. Let me be lazier. What is, if you follow the notation here, what should h1 of t naught and what should h2 of t naught actually be? What are their values? A and B, right? This is A, this is B. So what's x minus A? X minus A is t minus t naught times h1 prime of t naught, right? Y minus B is t minus t naught h2 prime of t naught. Oh, okay, fine, plus the remainder term. Plus the remainder term. I could throw away the remainder terms and just write approximately, you know? Many of you are engineers. That would constitute a proof, right? Okay, so then what? Many of you aspire to be engineers. Sorry. Me not put the cart before the horse, or the 300 level engineering class you want to pass, whatever. All right, so f of a comma b, and then plus fx of a comma b, and then what goes here? X minus a is what? Sorry, I'm still being, I need to be slightly more lazy here. So let's define h of t is equal to f of r of t, all right? So what's h of t minus h of t naught? It's f of oh, sorry. Well, that would be f of h1 of t comma h2 of t minus f of a comma b, all right? That's equal to what? So I subtracted the f of ab to the other side basically, and then so then I have fx ab times x minus a. We agreed x minus a was what? What was it? It was t minus t naught, right? Man, something seemed wrong here. right, well, I'm going to keep going with it here. Something... I don't want the t... The thing that's bothering me is the t minus t naught. I'm not happy about that. Yeah, I thought that should be there conceptually.
Is that the x minus a part of it? Whereas x minus a is just h1 prime t naught.
Well, I mean, the tangent line is the value plus the change in the, independent variable times the slope, right?
Right.
So x minus a is this plus the remainder. Oh, I know the problem. I'm an idiot. It's fine. It's fine, guys. So when we differentiate, when you want to calculate h prime of t naught, what do you have to calculate? What I've written right here is the change in h, right? Here's a formula for the change in h. But what's h prime of t naught? It's equal to the limit as t goes to t naught, right? Of what? The change in h, right? Divided by t minus t naught. I'm forgetting, I have to divide. It's a difference quotient. I have to divide by t minus t naught. I should be happy those are there. If those were not there, we would be in big trouble. Right? So this, the t naughts cancel, and you're left with fx ab h1 prime of t naught plus fy of ab h2 prime of t naught, which you can recognize as the gradient of f at the point AB dotted with, dh1, stupid notation, h1 prime of t naught, comma, h2 prime of t naught. And, of course, this was, A and B were what? Anyway, long story short, this is the gradient of f, unraveling, putting the notation back. This is h1f, the gradient of f at r of t naught, dotted with dr dt at the point t naught. I have to introduce the fixed but arbitrary point to make the argument because I need to use the linearizations of the multivariate function with the tangent plane and of the component functions with their respective tangent line approximations. If I didn't introduce the arbitrary point, the arbitrary time t naught corresponding to arbitrary point AB, it would be harder to see these formulas because you'd be tempted to use x and y both as the point and as the variable, and that's why I have to. It's annoying, the notational burden of introducing those extra points, but it's essential to be able to see what's going on here. To summarize the argument, all I did was I took the linearization of the function of two variables, which is given by basically the tangent line approximation, and then I just took the x minus a and approximated that with its the corresponding linearization of the x component function and the corresponding linearization of the y component function over there. And what ends up happening is you end up just taking the dot product of the gradient of the outside function with the velocity of the path, which is what we used last class without any proof. But any questions? There's probably a cleaner version of this in your book somewhere. This is not in my notes. In my notes, I refer you to a more general chain rule, which I teach in advanced calculus, which does this for basically arbitrary compositions. And but the argument's the same. The argument is simply that if you take one function and you take another function and you look at their derivatives, the derivatives are the best linear approximations. And so if you look at the best linear approximation of a composite function, it turns out that the best linear approximation of the composite is simply the composite of the best linear approximations of each piece. And turns out that you just multiply the matrices of the corresponding Jacobians and outpop all the chain rules that we're gonna see today. But I'm just telling you that in case you're interested. Come take advanced calculus. You'll see it there. That's not all advanced calculus. That's about a day in advanced calculus. We do more interesting things than that. But anyway, I digress. Okay, so chain rules. We can draw a picture of what we've been doing so far, all right? We basically have two examples that we've mostly done. We start with t, and we've got like intermediate variables x and y, right? And then those come back down and give you z is f of xy, right? And so if you calculate d dt of f of x of t, y of t. By the way, some people would insist that you should use h1 of t and h2 of t here rather than x of t and y of t. And I just don't do that because I think it's confusing. I think it's better to use x and y here with the understanding that they're functions of time, right? So I'm overloading the operator, if you will. X. I'm using x both as the variable, the intermediate variable, but also the function of time. And so when we do this, we get partial f partial x, dx dt, plus partial f partial y, dy dt. Right? What happens if you add another intermediate variable? Well, usually I write. Sorry, my picture. I should put the x down here and the y down here. I don't usually use these pictures. I'm going to give them a try this semester. See if you guys like them, like that. And then so coming back down here. So what happens is you just do what? So I just add one more argument, right? Then I just have partial f, partial z, dz dt, right? Okay. How about if I have more than one independent variable? What if I've got, say, a variable u and a variable v? These are both independent. Right? And then maybe I have intermediate variables x, y, z. Right? And then those come down to give me w, which is some function of, say, x, y, z. So you guys tell me, if I was to calculate partial u of f of x of uv, comma y of uv, comma z of uv, what would the rule be? So these are so-called intermediate variables. They're in the middle. The bottom one is dependent. The z is the dependent variable here. Oops. Sorry guys, I added the green. When I add the green, this is no longer sensible, right? What do I have to replace that with in order not to violate various terms and conditions of this class? W is f of x, y, z is what I'd have to go with. Something like that. If you don't like W, you could use Pac-Man. I don't care, whatever. Z is used in a different sense, though, so we're stuck with that. All right, so what we do is check it out, it's just this, partial f, partial x, partial u, plus what? Mm-hmm. Partial f, partial y, partial u, plus partial f, partial z, partial u. There's kind of some sort of like conservation of partials here. Like there's a balancing of x's. See this? See the balance? And there's like x's and x's and y's and z's and z's. And there's always a leftover u, like over here, right? There's a pattern here that you can kind of, if you pick up the pattern, it's easy to write these down. What would the derivative look like for if I put a z here instead? Right, so it's the same silly thing. Partial f, partial x, partial v, partial f, partial x, y rather, partial y, partial v plus partial f, partial z, partial v. So this is the chain rule for a function of a function of a function. Well, two variables. Let's look at an example. So suppose w is equal to x squared plus yz cubed, and suppose x is equal to u squared plus v squared, and let's suppose y is equal to the sine of u plus the hyperbolic cosine of v. What's partial w, partial u? So I'm going to write down the answer partly in terms of intermediate variables, and so let's see here. So first of all, I have 2x times something plus z cubed times something plus 3yz squared times something. Wait, what is z equals to is a very good question. That's a very good question indeed. Z is equal to what? Let's see, I don't think we know how to differentiate cosecant of uv there. I'm working on my Calc 1 review today. So you start throwing out random functions to throw into my examples. We got sine, cosh, cosecant. I'll try to get more in the next example. Did you see what I did so far? The things that I've written in blue, they're precisely, what are the terms? I mean, they're in terms of the general rule, they're these intermediate derivatives, right? Now what I'm going to put in parentheses is the partial x partial u, the partial y partial u, the partial z partial u, which is what? Partial x partial u, 2u. What's partial y partial u? Cosine u, all right. And partial z partial u? It is minus cosecant uv, cotangent uv times v. Yes, very good. And there you go. If I said you can leave your answer in terms of intermediate variables, you'd be done. I'm going to be leaving a lot of answers in this lecture in terms of intermediate variables in the interest of doing more than two examples in an interesting way. What would be partial w, partial v then? So this part stays the same, right? Because it's, you notice that both of the chain rules, that they have the same intermediate variable derivatives of the total function, of the dependent variable, which in this case is w. So I have to multiply by different partial x, partial v, partial x, partial y, partial v. So partial x, partial v is what? So you got 2v. We've got sinh of v. And over here, we get ourselves a minus cosecant uv, cotangent uv, times what? U, right? There you go. Es bueno? Well, I mean, what? Oh. See if I can make up another example here. Suppose we have w is equal to 2 to the x plus the natural log of y plus the, let's see, something unpleasant, log base 10. Ooh, there's one, of z. I think that's enough badness. And let's see here, let's let x be equal to, and y equals to something, and z equals to something. What do you guys want? Name a function we haven't differentiated yet this semester. e to the x to the x squared. Why did I ask? Fine. Okay, so u to the u. I'll take it. And then u to the u. How about the inverse cosine of v plus u? And how about, I don't know, inverse hyperbolic sine of square root of u. There, that's pretty awful. So partial w, partial u then. So let me just sketch the general pattern. We do partial w, partial x, partial u, plus partial w, partial y, partial u, right? Plus partial w, partial z, partial u. Let's see here. So derivative with respect to x of that expression is the natural log of 2 times 2 to the x. I don't know if you knew that or not. Well, there it is. Partial x, partial u, I feel like I need this much space for. Plus partial w, partial y is what? Yes. 1 over the natural, 1 over inside function y plus log base 10 of z. And then I need to make room for partial y, partial u, which I feel like I need this much space for. All right. And then partial w, partial z. Oh, yeah. Very good, very good. So 1 over y plus log base 10 of z. What's the derivative of log base 10 of z with respect to z, guys? Do you guys forget how to do it? Let us rederive. If I have log base 10 of x is equal to y, what does that mean? That means that x is equal to 10 to the y. So that means that 1 is equal to the natural log of 10 times 10 to the y dy dx. No one complained when I threw down natural log of 2 times 2 to the x, so I assume that you guys remember that. So I'm allowed to do that. That being said, there it is. So dy dx is 1 over natural log of 10 times 10 to the y, but 10 to the y is equal to x. So there you go. So basically, I have to divide by the natural log of 10. Okay. So what's partial x partial u? Let's see here. This, in other words, what's d to u of u to the u is equal to what? I don't know. Let's let, I need some variable. Let's say theta is equal to u to the u. That means the natural log of theta is equal to u natural log of u, which means that theta, 1 over theta prime is equal to natural log of u plus u over u, which is 1. So there you have it. Theta prime is equal to the natural log of u plus 1 times u to the u. There's your derivative. So natural log of u plus 1 times u to the u. In other words, we do logarithmic differentiation for such a thing. What's the derivative of inverse cosine? Man, you guys are making me work today. So let's say theta is equal to inverse cosine of stuff. I'll just work the derivative out for x for a second here. So what, cosine of theta is equal to x. Differentiate both sides. Minus sine theta, theta prime is equal to 1. Theta prime minus 1 over sine theta, also known as minus 1 over the square root of 1 minus cosine squared theta, aka minus 1 over the square root of 1 minus x squared. Now, how did I know it was negative? Well, that's easy. Inverse cosine is the branch of the cosine. It's the inverse for cosine restricted to 0 to pi. Cosine from 0 to pi is decreasing, so its derivative must be negative. Hence, I must choose the minus there. In other words, this is the derivative of inverse cosine. So what's this derivative? It's minus 1 over the square root of the inside thing squared, 1 minus the inside thing squared. Notice that that's it, because the partial derivative of the inside function v plus u with respect to u is just what? There's no other term there, because partial u of v plus u is just 1. So I just, that's that. Ah, man, this example. Fine, what's the derivative of inverse hyperbolic sine? Who started this? I shouldn't have made that promise. I'm starting to regret that. I told one of you I would try to work in all of Calculus 1 today. Maybe I shouldn't have agreed to that. Is it too late to rescind my promise? No. Dang it. Some of you are enjoying my suffering. Fine. Actually, it's not suffering. I love this stuff. Cosh of theta prime is equal to 1. So I'm working on the derivative of inverse hyperbolic sine. So I play the same game I just played. I set a variable theta equal to the inverse function that I'm interested in the derivative of. I take the function of both sides to change it to a problem about differentiating the function. I know how to differentiate hyperbolic sine. I know it's just cosh, but the chain rule says I have to do cosh of theta times theta prime. And so what that gives me is theta prime is 1 over cosh theta. But hey, everybody knows that cosh theta is 1 over the square root of 1 plus sinh squared theta. Well, isn't that convenient? Because that just happens to be 1 over the square root of 1 plus x squared. So there you go. The derivative of inverse hyperbolic inverse hyperbolic sine is 1 over the square root of 1 plus x squared. That's positive, which is encouraging, because sinh is always increasing. The derivative of sinh is cosh. Cosh is always larger than 1, which means sinh is always increasing at a rate of 1 or larger. So I don't know if you guys knew this or not, but the derivative of a function and the derivative of its inverse must be equal, and they must be matching. If a function's increasing, its inverse function at the corresponding point is also increasing. If a function's decreasing, its inverse function at the corresponding point is also decreasing. So if I know that sinh is increasing, inverse hyperbolic sine must also be increasing, which is why I could choose the positive square root. You see, when I went from here to here, there's an ambiguity of sign that you might worry about. I guess you could also say, well, cosh is positive, so it has to be that. Well, fine, you got me there. Oh, man, there's a square root inside of it. Ugh, fine. So this is 1 over the square root 1 plus x squared, but what was x here? It's this thing, right? So square root of u squared, that's just u. Then I have to multiply by the derivative of that, the derivative of the inside function, which is square root of u, which gives me a what? Yes, times 1 over 2 times the square root of u, and there you have it. If you don't mind, I'm going to leave my answer in terms of intermediate variables because I really don't feel like putting in x, y, and z as what they are. No. Only a fool would put this on a test. Why? No, because a test is something you have to grade. It's not about you guys. It shouldn't take too long. It's not that long. I mean, come on, it's differentiation. What is the thing about differentiation? I mean, you put down almost any formula you can think of, right? Can you differentiate it? If you're up to date, if you've paid your dues, if you've been paying attention, if you're aware of the standard category of tricks and stuff, you can do it. It's just a matter of application of rule after rule after rule, right? So it's just, do you want to do it? Yeah.
How come instead of like partial x, partial u, and partial y, partial u, aren't we just doing like dx du, like dy du? Didn't we just do like regular derivative?
Well, since x is here, I can add something to the original problem statement without changing the answer. I can add plus v to the v squared. Are you happy? Oh, he's not paying attention. Okay. I could do that, but it wouldn't change anything because partial derivative with respect to u doesn't even pick it up. That's a constant. So that's the difference between this one and the one we started with today, is that x is a function possibly of two variables, right? Some of my examples have been too stupid. Like z doesn't have any v dependence either, right? I should have added, I don't know, 1 over the square root of the square, 1 over v plus the square root of plus the square root of v or something. I don't know. It wouldn't have changed the answer. All right, another example. I think it's it might be worth just a second to explain where these chain rules are coming from a little bit. So let me look at this. So suppose we have a function from R2 to R. All right, and then I've got another function, let's say t, which is going from R2 to R2. And just to give you a sense of the variables here, this has xy variables. This is the z variable. This one is starting with u and v, and then it's going to x and y. So I'm thinking about something like z is equal to f of t of uv, where t is actually equal to x comma y. Like x and y are the component functions of t. So with this setup, all right, the Jacobian of f is just the gradient of f, essentially written as a column vector. So it's actually partial f partial x, partial f partial y. All right. The Jacobian of t here, it's a little bit more interesting. It's a 2 by 2 matrix, but it's partial t partial u, partial t partial v. All right. So what is that? Well, that's the first t is xy, right? So I mean, that's my sneaky notation. This is actually a column vector. It's x with y over it, like that. So partial t partial u is like it's partial x, partial u, partial y, partial u. So u derivatives in the first column, and then partial x, partial v, partial y, partial v, like that. What happens when I multiply these matrices? So what happens if I calculate the multiply the Jacobian of f times the Jacobian of t? What do you get? If you don't mind, I'm going to use the subnotation fx, fy, and then this matrix can also be denoted x sub u, x sub u, y sub u, x sub v, y sub v. It's a nice shorthand rather than writing partial, 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 blah, 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 blah. You get it. So I don't know, you guys may or may not know how to multiply these matrices, but if you do, the first thing I get is fx xu plus fy xu, and then the second thing I get is fx times xv plus fy times yv. Okay, fine. So I'll go back to the other annoying notation. So I got partial f, partial x, partial u, plus partial f, partial y, partial u. And this one is partial f, partial x, partial v, plus partial f, partial y, partial v. What you're looking at is the Jacobian of f composed with t. Well, this is the general chain rule. In the language of Jacobians, the chain rule simply says that to get the Jacobian of the composite, you multiply the Jacobians of the things being composed. Now, technically speaking, I'm supposed to take the Jacobian matrix of f and evaluate it at t of x of uv, y of uv. But this, on the flip side, would be just, partial z, partial u, partial z, partial v. So that's just the chain rule we've been using. Partial z, partial u is this stuff. Partial z, partial v is this stuff. And so all these chain rules I've been writing for you today, you can see from just multiplying the Jacobian matrices of the corresponding functions if you want to. Yeah.
Is that a typo right above the green line? We have f sub y, x sub u. Should that be x sub y, y sub u?
This one?
Just here left. That term. He's down below that.
Oh, that should be a y. Yeah, definitely. Anything else? The other reason I'm showing you these Jacobian matrices a little bit is they come up again later when we study change of variables and integration. It turns out that the determinant of the Jacobian matrix tells you how the volume rescales when you change variables of a triple integral or a double integral or whatever. So they're the tool you need to linearize functions of several variables. Okay, well, anyway, let me get back down to earth over here. Why do we care about taking partial derivatives of more than one independent variable? Like, what's that about? What did we talk about? Remember that unpleasantness that we had in the first week when I tried to teach you the whole course in the first week? Remember that? Well, I mean, I do show you pretty much all the algebra we do the whole semester very early on. That's part of the reason my course seems harder than some other people's at times. But one of the things we did was something like a parameterization, right? So R of uv could be what? Could have been something like, I don't know, I guess it could have been something like u comma v, u squared plus v squared. Now, this technically is what? I mean, here you're looking at a function which is taking in something from R2 and it's going to R3. Can you tell me what this is, though? This is a parameterization of what graph? Yeah.
If I'm reading it right, it's growing up like an upward feeling. It's growing inwards.
Oh, but it's got u and v. if I rewrite it as a graph, z is equal to what in terms of x and y? X is equal to u, y is equal to v, right? Z is u squared plus v squared, so z is equal to x squared plus y squared. So what we're looking at here is what? It's just the parameterization of the paraboloid. So what would the geometric significance of, say, partial r partial u be? How would you calculate that? What would this mean? We haven't done one like that just yet. I just changed the rules of the game on you, didn't I? We were differentiating functions that were real valued. Now all of a sudden I'm differentiating a function which is vector valued. But you probably already know what to tell me. What's the answer? Should be a vector, right? 1, 0, 2u. All right. What would partial r partial v be? Partial r partial v be, yeah. Yeah, 0, 1, 2v. If we pick a particular point, right? If you think about taking a particular point on this paraboloid, right? Say this point right here. So suppose that's r of u naught v naught. What's the geometric significance of these two vectors? How would we define partial r partial u, by the way? What's the definition of that at the point u naught v naught? It would be, I would say, differentiate with respect to time, r of u naught plus t, comma v naught, and then after that's all done, plug in t equal to 0, right? In other words, you vary the u component, you leave the v fixed, but what is that? What is the thing? What's this? It's what? It's a path, right? On what? On that somewhere, I don't know exactly, but maybe it's something like this, right? That's this path where on this path we have fixed one of the parameters. So maybe v is equal to v naught on that path. And so what this is the tangent vector to that path, right? That's partial r, partial u at u naught v naught, right? And how about the other one? Well, the other derivative we're looking at, what's its significance geometrically? There's some other, I don't know exactly what it looks like, but it's some other path. Maybe that's u equals to u naught, so the u is fixed, and there you've got some kind of partial r partial v, because v is the variable on that path, right? So how would you find the tangent plane then? Yeah?
Are you thinking in a parametric form with two independent variables?
Oh,
It's pretty easy to do. You have two vectors on the plane.
Luke has given me a properly lazy answer. I appreciate that. So I was asking, what's the tangent plane here, basically, right, attached to this point? My picture is starting to get cluttered. So Luke is like, well, that tangent, you already have two vectors in the plane. I could call this thing B, call this thing A, and he's just like, the tangent plane, it's just something like, the point in question plus, say, u times a plus v times b. And if you just take all possible things like that, then there you have it. That's the tangent plane. And Luke is right. That's a parameterization of the tangent plane. Absolutely. What's its Cartesian equation? What's the Cartesian equation of the tangent plane in this example? So what I want to do is I take these coordinate, these are called the coordinate velocities. This is the partial, they're sometimes called partial velocities. This is the u partial velocity, that's the v partial velocity. Those lie tangent to the plane, they're actually lying in the tangent plane. You just take the cross product of those, and that will give you a normal to the plane. So the normal vector field, as it's sometimes called. So you can define n of uv equals to partial r partial u cross partial r partial v. And while I've just discussed how to use the normal vector field to find a normal at that specific point u naught v naught, if you think about what this is, this gives you a vector field which is attached to a parametric surface, which is always perpendicular to the surface. I don't know if you're keeping score or not. That's a third way to calculate a tangent plane from various different characters. What are the three characterizations we have of a surface in here? Yeah, so we had level, we had graph, and we had parametric. Graph is kind of a middle ground. Let me just draw together our thoughts on this. Level is something like you have a level function, f of x, y, z equals to some constant, let's say k. To find the normal vector to the tangent plane, gradient of f at the point P is normal. All right? Graph, it's kind of an oddball. Z equals f of x, y. All right. Parametric was what? Something like r of uv is x of uv, y of uv, z of uv. So over here to find the normal, we find the normal vector field n of uv. We just take the cross product of the partial velocities. That gives me a normal. If you pick a particular u naught v naught, what is it?
Is this like a different way to find the equation of the tangent plane?
Yes.
Or the normal, or are they the same?
Well, the equation of the tangent plane is totally wrapped up in what the normal is. Right? Once I know the normal is ABC, and I know a point, then the normal is a times x minus, the x coordinate of the point, b times y minus the second coordinate of the point, the base point, and c times. So once I know the normal, I can write down the equation of the tangent plane. I'm getting there though. But the first order business, what's the normal? Actually, for the graph, it's kind of weird, right? We kind of skipped over the question in the case of the graph of what the normal was, right? And what did we go straight to? We went straight to saying, well, the equation of the tangent plane is z is equal to f of ab plus fx ab. Oh my goodness, so much writing. X minus a plus fy. Ah, curses. I can't fit that stupid thing in there. My stupid. All right, z is equal to f of ab plus fx ab times x minus a plus fy ab times y. Sorry, this is really, I don't know if the camera's going to be able to pick up on this. I'm writing the equation of the tangent plane that we had last time, right? If you look at this, what's the normal for the graph? I mean, it kind of depends on how you want to look at it. you could either subtract z to the other side or subtract the fx and fy. If I rewrite this, say I could rewrite this as like z minus f of ab minus that equals to 0. If I did that, then in retrospect, you can see that the normal was what? It was minus fx at the point minus, let me not write the point dependence, it's cluttering everything. So it was minus fx minus fy and 1. So, the equation down here would be what? It's fx of p times x minus a plus, well, I don't know. Tell you what, can I just not write the equations down there? Do you know what I'm saying? Once you have the normal, you can write down the equation once you pick a point. If I have x naught, y naught, z naught equals to k, then what I do is I have f sub x. I need to call this thing. Let me call this point p naught. F sub x of p naught times x minus x naught plus f sub y of p naught times y minus y naught plus, I just can't fit this in here, f sub z of p naught times z minus z naught. That would actually be the equation of the tangent plane, right? If you'll allow me this, let's suppose that n of u naught v naught was equal to abc, okay? And let's suppose that, r of u naught was what? X naught, y naught, z naught. Then what would the equation of the tangent plane be? All I'm saying is once you have the normal, you go back to what we did the first week, right, or the second week, and you use the normal for the coefficients of x, y, and z respective, and you take the difference with the base point that you have on the plane. Now the base point in these different viewpoints, it's either a solution to the level surface equation, right? It's a point on the graph, or it's just something that comes out of the parameterization of the surface. We have these 3 different viewpoints of how to understand what a surface is geometrically, right? I think it's helpful to see some pictures of what I'm talking about, though. See if I can find some. I could do partial derivatives another, hour of class like we were doing at the start, but I think you'll get just as much out of just like reading the notes quickly and then trying to work problems for yourself, so I'm not going to waste your time by showing you more of those. We've seen some pretty horrible ones. I hope that suffices. Now, I had the homework being due Monday. I'm moving it to Tuesday because I want to give you all of Monday to ask questions about it. Because I told you, I indicated tomorrow there was no class. And I'm going to stick to that because you guys have been very good. And we've met a lot. And I think we should be allowed to take a day off here and there. So, you guys should be upset. I'm cheating you out of math. Why aren't you guys outraged? Where's your fury? Oh. You have other things on your schedule? How dare you, sir? There's only my class.